Today we'll take our first foray into the contents of the black box and introduce the fundamentals of neural networks by breaking down the components of a standard neural network, or so-called vanilla neural network. Our objectives are as follows. Introduce the basic architecture and motivation behind artificial neural networks within the context of supervised learning. Understand the individual steps within a single iteration of the learning process, including the forward pass, cost calculation, and backward pass. And finally, learn to identify the components of a neural network diagram and name them. Recall that within a supervised learning context, the purpose of a model was to input data and output a prediction label or value that approximated the ground truth target. We've previously treated the model as a black box. Let's open up the box and begin to understand its contents. First off, how do we define a neural network? A neural network is a computing system inspired by the structure of biological neural networks. It is made up of a number of simple, highly interconnected processing elements, which we will call nodes. The purpose of this computing system is to progressively improve performance on a given task without task-specific programming. So let's now introduce a neural network and begin breaking down its individual components and processes. Broadly, we see that the network is composed of layers, of which each layer contains several computational nodes. We'll first deal with the input and output layers. Recall that we use the notation big X when referring to the entire set of training examples and big Y when referring to the entire matrix of target values. In this case, we use big Y hat to denote that we are talking about model predictions for all examples. Let's take a look at a single training example, which is denoted by a small x, and the prediction by small y hat. Recall that the superscript value enclosed in parentheses simply indicates which example in the dataset we're focusing on, and is not an exponentiation. As discussed before, our imaging study can be represented as a column vector which contains all the individual pixel values of the image. For the first layer in the neural network, the input layer, each node represents a single feature from the input column vector. In this case, each feature is a pixel value. We can denote each individual feature by a subscript. For example, x sub 1 indicates the first feature in the column vector, and so on and so forth. Let's fill in the values for these features. There. To simplify the example, here we will only deal with 3 pixel values, but recognize that in a real-world model of this architecture, there is an individual node for every pixel in the image. The node in the output layer can be viewed as a mathematical function that receives the output from the prior layer as its input, performs a computation, and outputs a predicted class or value. The choice of function depends on the task at hand. Now we will discuss the nodes in the layers between the input and output layers, the so-called hidden layers. Let's momentarily view the world from the perspective of a single node in the hidden layer. We'll discuss the ideas in an abstract sense so that we can generalize these concepts to most models. The node takes in as its inputs the outputs from the prior layer. Because in this discussion we are describing a node in the first hidden layer, its inputs will be the features from our input column vector. Each of these features is associated with its own weight. Now, the node itself is associated with a bias term. The weights and bias are collectively termed parameters. Now, using the input features, their respective weights, and the node's bias, the node will perform 2 computations in series. First, a linear function is computed. The output of this linear function, which is by convention denoted z, is then input into a nonlinear function. The output of this nonlinear function is by convention denoted a for activation. Of note, the nonlinear function itself is often referred to as the activation function. The choice of activation function can vary, but is a topic for later discussion. The output activation of this node then serves as the input to the nodes in the subsequent layer, and so on and so forth. The difference in color here indicates that the parameters which are designated by the same letter hold different values for each node. For example, this weight differs from this weight. Now let's take a step back and look at the network level. Note that for a given layer, there are multiple nodes performing these functions in parallel. each with their own set of inputs and associated weights and bias. Now, across layers, these computations are occurring in series. That is, the outputs of prior layers are fed in as inputs to the subsequent layers. This process continues until a final prediction is output. This entire process, viewed from left to right graphically, is called the forward pass. Once we have an output prediction, we need to compare its value to the target value. This comparison is made by passing the predicted value and target value into a cost function, which outputs the difference between the two. Like the activation function, the chosen cost function varies depending on the problem type, and is also a topic for later discussion. Now that we've computed the cost, we'd like to find a way to update our weights and biases so that after the next iteration of this process, our predicted value more closely matches the target. The task of defining a cost function, also known as an objective function, and iteratively minimizing it is a subset of a class of problems known as optimization. In the context of a neural network, this process is performed by computing the partial derivative of the cost function with respect to all the parameters in the model, and is known as the backward pass or backpropagation. The result of this process is called the gradient, which for now can be loosely viewed as a mathematical object which packages the information we'll need to update our weights and biases most effectively. Understanding this process usually requires some time and repeated exposure, so we will deal with it in more depth in the next lecture. For now, understand that the backward pass is an effective way of identifying how to update our weights and parameters to maximally decrease our cost at the next iteration. Once we've updated our parameters, we then repeat the entire process. Some vocabulary. An iteration is one cycle through a forward and backward pass. An epoch is one cycle in which the entire dataset has been passed through the network. If for each iteration we input the entire dataset, the number of iterations equals the number of epochs. There are situations in which we do not feed the entire dataset into the network at once, but do so in batches. In these instances, it will take multiple iterations before the entire dataset has been passed through the network. For instance, if we have 100 examples in our dataset and feed them in 20 at a time, it will take 5 iterations per epoch, since 5 iterations of 20 examples per batch will cover our total of 100 training examples. Now let's practice using neural network nomenclature. The number of layers in a network is defined by the number of hidden layers plus the output layer. In this case, we have a 2-layer network. The number of input features is indicated by the number of nodes in the input layer. Here, 3 input features. For a given hidden layer, the number of hidden units is indicated by the number of nodes in that layer. Notice that a hidden unit and a node are synonymous when we are discussing the hidden layers. The number of output units is denoted by the number of nodes in the output layer. Now try this example for yourself. Feel free to pause the video, then compare your answer. Let's recap. For now, let's assume we pass the entire dataset into the network at every iteration to avoid confusion. For each iteration, we take all the data from the training set, pass it into the network, generate a prediction for each example, and then calculate the total cost across all training examples. We then calculate the gradient of the cost with respect to all network parameters and use the gradient to update our weights and biases. This process is repeated until our cost converges at the minimum. We will learn more about this process in the next lecture. In summary, we've introduced the basic architecture and motivation behind artificial neural networks within the context of supervised learning. We've understood the individual steps within a single iteration of the learning process, including the forward pass, cost calculation, and backward pass. And finally, we've learned to identify the components of a neural network diagram and name them.